Okay, let me introduce Wolfgang Porod, who is going to take a digression back to devices momentarily. And in this case, it's nanomagnetic logic. I should say, of course, nanomagnetism is used for storage, so why not use it for logic as well?
Thank you, Eli. I'd also like to thank Jeff Bokar for the opportunity to be here. And I have to admit, it's a little bit intimidating to stand up here and talk about adventurous ideas. This is a pretty tough crowd, but I'd also like to mention that there's some very interesting work going on at Berkeley in the group of Jeff Bokar along these very same lines. As Eli already mentioned, we all know that magnetics, for the most part, is used for data storage, but not so much for logic. So this work is in the context of patterned magnetic material, just like MRAM technology, where patterned magnetic islands are being used to represent binary information. However, what you don't want for data storage is coupling from one element to the next. Obviously, this gives you crosstalk, gives you interference. And so the basic idea of what we're talking about, what I'd like to tell you about here is to try to take this nuisance for data storage and try to make it a feature. So in other words, try to see if we can take this coupling and we can do logic with that. And I'll tell you some of the thinking and some of the work that we have done at Notre Dame. And again, there's some work going on at Berkeley along these lines. I thought I'd start out to say a little bit more. George Buryanov, already earlier this morning, talked about some of the research that's going on within the Semiconductor Research Corporation, which recently, let's see, is this a pointer? Which recently founded a new entity, the NRI, the Nanoelectronics Research Initiative, to essentially address what this workshop is also about, some of the fundamental limits that micro and nanotechnology, electronics in particular, is facing. By and large, logic is being done by using currents and voltages. So we use essentially one property of the electron, namely the charge, in order to do logic. And so part of the thinking is, well, the electron has also other properties like spin. Why can't we look spin or some other state variables to represent information? And so this is really the thinking behind the NRI. About 2.5 years ago now, the first center, NRI center, was started on the East Coast with IBM strongly behind it. Many of you will know that this is the center hub at Albany. The second center was founded on the West Coast, and some of the researchers represented here are part of the center. The third one, about 1.5 years ago, was started in Texas around UT Austin. And then just about 1 year ago, the fourth center, the Midwest Center, was started, which is hubbed at Notre Dame with some other Midwestern universities participating. And so I'm going to tell you some of the research that is going on at Notre Dame along these lines. I would also like to mention that part of the effort, the center effort that we are undertaking, is trying to benchmark some of the device technologies that are being developed as part of the NRI and try to compare them against each other at a functional level. And there's going to be a workshop that will be held at Notre Dame in mid-August, August 18th, where these ideas and where this benchmarking is going to be discussed. And I wanted to invite you, if you're interested, to come and join this workshop, again, mid-August. So after we've been thinking about doing or exploiting magnetism for logic, I came across one of the early books on computer design, which was published in '67. And I was kind of surprised to see at that time that in the early days of computer design, magnetism was actually used, so magnetic state variables, for the design of computers. And so taking from this book, magnetic phenomena are attractive because they hold state, which of course is what's behind the applications of data storage. One can also do logic, and one can also do amplification with magnetic phenomena. As a matter of fact, one of the early computers, the Elliott 803, used magnetic elements, magnetic cores. All of you are familiar with those for data storage, not only for data storage, but also for logic. And so you can see that if you string wires one way or another through neighboring cores, you can affect logic functionality. I mean, of course, with the shrinking of technology, this kind of way of doing logic was not competitive with semiconductor technology. But what's behind our thinking now is maybe instead of stringing wires in order to communicate from one magnetic element to the next, now the magnetic elements can be made very small. As a matter of fact, in the single domain limit, I'll say more about that. Maybe one can use the same ideas of using logic based on direct physical coupling and not by stringing wires between magnetic elements. And so the basic architecture idea of using physical coupling for short range or for local interconnectivity actually goes back to some of the other work that we had done at Notre Dame now more than 10 years ago, which we termed quantum dot cellular automata. And this work really was motivated by the early to mid-90s by the emerging capability of using quantum dots and occupying quantum dots with few electrons. And so we were motivated at that time to think, well, what could you do? Assume that you have a technological feasibility to fabricate structured arrays of quantum dots, populate them with few electrons. What could you possibly do? And so the basic idea of this QCA scheme is the following. Assume that you have a cellular array where each cell in this array consists of a few quantum dots, 4 in this example. And assume further that you're able to occupy each cell by few electrons, say 2 electrons in this case. Within each cell, then, you have an interesting dynamical problem. The electrons are confined to sit on the dots, but they can jump between the dots. The electrons are going to feel the mutual Coulombic repulsion, and you're going to have 2 basic configurations, a configuration like this and a configuration like this. You can think of it as click and clack. So in other words, the basic idea here is to represent information not by voltages and the flow of charges, but by the arrangement of charges, but by a configuration of charges. Furthermore, if you assume that you can place a line of cells in a linear array like this, obviously a configuration like this is going to be preferred over the ones where the neighboring cell is in an arrangement like this, again, because of the mutual Coulombic interactions from one cell to the next. And so at that time, in particular, Craig Lent and I did some simulations. And so with a scheme like that, you can have binary wires where information flows down the wire. So it's just the arrangement, the configuration of electrons that changes, but there's no net flow of charges down this wire. And that's the reason why a scheme like that inherently is lower power than using wires to communicate from one element to the next. With certain arrangements, you can effect a binary logic functionality. As a matter of fact, it turns out that the native logic in this QCA scheme is just an intersection between 2 lines. And the native functionality is that of a 3-input majority vote. If you think of these 3 here as the input cell, then the output, which is this cell here, represents the majority vote of the inputs. And all of it is driven just by physical interactions. We've done simulations of that. Here you see the truth table. And from a computer, or from a design point of view, such a scheme is interesting because a 3-input majority vote has hidden in it Boolean and Boolean OR functions. If out of these 3 inputs, you view one as a set gate, say A in this example. So if A is 0, then both B and C have to be 1 in order to have a 1 at the output. So by setting A to 0, the A input to 0, you have reduced this majority voting gate to an AND gate. Similarly, if you set A to 1, then only either B or C have to be 1 in order to have a 1 at the output. Now, in terms of physical implementations, we have looked at different possibilities. One of the early implementations, I'm not going to say too much about that. Some of you may know about it. Was not based on quantum dots. Quite frankly, the technology in order to realize a scheme like that was not quite there. However, instead of dealing with single electrons on quantum dots, you can also place single extra electrons on metallic dots. So one of the implementations were single electron tunneling structures. The drawback of that, obviously, is that you have to, based again on the capacitances of the junction that you're dealing with here, these experiments were done at very low temperatures. So those were heroic science experiments. However, from an application standpoint, perhaps not really that interesting. We've also worked with chemists who have collaborated with us on mixed valence compounds. So this QCA scheme also is a way of looking at molecular electronics where molecules are being viewed as structured containers of charges. So if you have a steric, rigid molecule like this mixed valence compounds, where at each of these corners you have a ruthenium atom, which acts just like a quantum dots, we have seen in experiments, cyclic voltammetry experiments, the jumping of the electrons between the corners, just like in the square quantum dot cell that I've shown you before schematically. In terms of applications, however, I think that magnetic implementations which use the same ideas, namely this physical coupling from one element to the next, so the same concepts apply if we replace electrostatic interactions by magnetic interactions. It turns out the first experiments along these lines actually came out of Cambridge University when Russell Coburn was a postdoc there. They were experimenting with lines, linear arrays of circular magnetic dots, and they observed like a kink propagating down the line, which was entirely driven by magnetic interactions from one element to the next. What Russell Coburn has done in the meantime, he has worked on magnetic domain wall logic. Well, see, if you think of these dots being washed out and sort of washing into each other, this becomes just a line, a magnetic line, and this kink here becomes a domain wall, which can propagate along a line like this. One of the problems in these experiments is that with a circular magnetic element, there's no preferred orientation for the magnetization. And so we have picked up on these experiments. And so we have dealt with elongated magnetic islands, and we're using the property of magnetism that not only the size of a magnetic element, but also the shape of the magnetic elements determines its property. See, if you have an elongated island like this, you have an easy magnetic axis, which is along the long direction. The magnetization likes to be in this direction. And you have a magnetic hard direction, which is along the short direction. So it is hard to keep the dot or to magnetize the dot along the short axis. The interesting thing here is that you have two basic configurations, one where both magnets are aligned, and the lower energy configuration, just like you would expect from bar magnets next to each other, is where the magnetization directions are anti-aligned. The interesting thing for us here is that the energy scales that we are talking about here are on the order of hundreds of KT. We've heard about KTs before earlier today. So all of this works at room temperature. And in order to go from one configuration to the next, you have to go over an energy barrier that is shown here. So if you have an external magnetic field and you bias your configuration such that the magnetization of the second dot is aligned along the hard magnetic axis, and you need a clocking field to do that, then there's only a small fringing field that can determine whether or not the right-hand dot switches to the left-hand side or to the right-hand side. And so this dot is sort of in a vulnerable state, and you can exploit that for switching, as I'm going to say a little bit more. So this scheme actually works. I'm showing you experiments here. So these are two magnetic islands next to each other. This shows the structure. This is an AFM image. Next to it, you see the magnetic contrast in a magnetic force microscopy image, and you see that the two are anti-aligned in the ground state, as you would expect. One of the key experiments, one of the early experiments that we did is we saw an alignment, this anti-ferromagnetic up, down, up, and so on alignment that you would expect in lines as long as 64 magnets, which gave us the hope that you might base applications on these phenomena. Now, I would like to emphasize the point that we are dealing with single domain magnets. So we are in a size regime where there's only one magnetic domain that fits into each of these islands. And I show you here a magnetic force microscopy contrast of an array of islands with different sizes and different aspect ratios. And you see that if the dots become too fat or if the dots become too small, then you are no longer in the single domain limit anymore. You break into multiple domains. And then, of course, the fringing fields from one dot to the next disappear. So you only have strong coupling from one element to the next if you are a single domain. And again, we can do some engineering for that, both with the sizes and with the aspect ratio. So that's an important point here. I was tempted, or I am tempted, to show this graph to you just to make the point again that we are in the single domain limit. See, it turns out that animals, and also us, have specialized bacteria, specialized cells that grow magnetic islands with exactly the right size and the right aspect ratio to be in the single domain limit. If they're too large, then you break up into multiple domains and you don't have the equivalent of a bar magnet anymore. If the islands are too small, then the energy required to switch these islands becomes so small that even random thermal fluctuations can change the magnetization, and then you're in the superparamagnetic limits. And so different animals like pigeons or tuna and so on grow these perfect single domain magnets and use them for navigation. And so the magnets that I'm going to be telling you about are somewhere in here. So we're somewhere between the pigeons and the tuna. So to tell you a little bit more about how we accomplish switching in arrays of magnets. So what I'm showing you here is a nice antiferromagnetic alignment in a line of cells shown here. And we have accomplished this by applying a clocking field. So we apply a clocking field in the horizontal direction. What this external clocking field does is it essentially bends the magnetization from the direction where the dots want to be in, which is the easy axis, into the hard axis. Once the point towards the hard axis, then a small magnetic field, which could be a fringing field from the neighbor, or it could be a fringing field from the input, pushes it into the correct state. And so within a scheme like that, we can also use horizontal dots as shown here, where the easy axis is along the lines of the clocking field. So if we apply the clocking field, all of these magnets here are nulled. The input dot is set. As we reduce the clocking field, the input dot keeps its magnetization, and all of the dots in the line here switch from the hard axis along the easy axis, right? And so you.
Why do you need this clocking field?
I'm sorry?
Why do you need this clocking field? Is it not only the remnant state, these things, that they add antiparallel?
You need the clocking field simply because the magnets or the energy barrier from one configuration to the next is rather large. So the clocking field, you can think of the clocking field essentially as reducing the energy barrier to get from one configuration to the next.
Okay, in remnants, it's not possible to get them so close that they are lining into the ferromagnetic.
That's correct. That's correct. So we can have lines of magnets that I've shown you before, which then do anti-line. Lines of magnets like this with a clocking field, again applied in the horizontal direction, tend to align head-to-head. So this is what we call a ferromagnetic alignment. And so this scheme works. So we have fan-out, which I show you here. So this, again, would be an input dot. This is the AFM image, and this is the corresponding MFM image, where you see that the magnets switch in the way that you would expect them to switch. We have also experimented with different arrays, and again, you see that the input dot is able to set the configuration of the magnets as we like, or as we design them for. I've told you before that in this QCA scheme, just an intersection of lines gives you 3 input majority logic functionality. The same works for a cross or an intersection between magnetic lines. And what you see here is all 8 configurations, or all 8 possible configurations of a 3-input majority gate, and so which demonstrates that a scheme like this works. We have also used shape anisotropy. In other words, that different switching fields are required to switch dots with different aspect ratios and sizes in order to set one of these inputs for a majority gate. So here are the 3 inputs to this intersection. This dot here is a little bit longer. So in other words, it takes a larger field to switch it. And so you can see that this is the dot which is longer here, that for different input fields which we apply, we are capable of not switching this input dot, which is used to set the functionality, if you want, of this 3-input gate, whereas the shorter ones actually switch, and the majority gate switches as designed. Now, of course, what you would like to have for an integrated system, you would like to generate local magnetic fields. And so we've spent some work recently on placing these magnets on clocking wires. So the idea here is that we have wires, copper wires, which are wrapped into a ferromagnetic yoke, similar to what is being done in MRAM technology, to focus the magnetic field which is generated by current pulses through the wires along the wire. And this is the magnetic field that we use for clocking the wire. We've also done a power analysis, just trying to compare how a scheme like that, using magnetism for logic, would compare to what's being done in silicon. And so there are essentially 3 inputs to the total power budget. One is associated with the hysteresis loss of the magnets. So in other words, in order to switch a magnet from one configuration to the next, you have to dissipate an amount of energy, which is given essentially by the size of the hysteresis curve. There's energy required to pump current through the clocking wires. And there's, of course, energy also that's associated with the circuitry, which generates the clock pulses in the first place. So looking at these different components now one by one, some time ago already, we did some simulations with George Chaba at that time. And it turns out that the energy required to switch the magnets is actually quite small. So in our simulations, our simulations show that you can switch 10 to the 10 magnets at 10 to the 8 times per second. And this array would dissipate only a fraction of a watt. So this looks very promising. However, it turns out that most of the power, at least in the scheme that we're using right now to generate the magnetic field, most of the power really lies in the wires that are used, 2 minutes, that are used in order to generate these clocking fields, in these magnetic clocking fields in the first place. We have not done a detailed analysis yet of the power budget, which is associated with the circuitry, the clocking circuitry, but we estimate that this power is on the order of a quarter of the power associated with the driving wires. One of my colleagues, Mike Niemeyer, in computer science and engineering at Notre Dame, has attempted a comparison with silicon. It's of course hard to compare a magnet to a transistor, and so we've attempted to make a comparison at the functional level. In particular, we have looked at the energy delay product for a 32-bit CMOS, for a 32-bit ripple adder. We've looked at CMOS experiments and CMOS projections, and we have laid out these structures also with the nanomagnets that I've just shown you. So here is the line that we found in the literature. We've also run the ASU simulator in order to project what the power would be. Comparing that to the power analysis that I've just showed you with the three components, with the hysteresis loss within the magnets and the clocking circuitry. And depending on what assumptions you make about the magnets, we are somewhere here with the sizes of the magnets that we are experimenting with right now. With the magnets getting smaller, the energy will also be reduced. Furthermore, so far we have worked primarily with permalloy and supermalloy, however, also working with different material systems. And Jeff's group here at Berkeley is looking at interesting material systems where a magnetic anisotropy, which is a material property, is exploited in order to assist switching. So there's some interesting work going on along these lines. Okay, so at this point, I would like to wrap up. I would like to thank my collaborators, which are listed here, and the funding sources which you see here. And so I would like to thank Jeff and Eli for the opportunity to tell you about I think a rather different way of doing logic using nanomagnets. Thank you.
I wonder if I could ask a question. So you talked about the wires, and there's actually quite a bit of energy in the wires.
Yeah.
And so that makes it similar to a lot of the other technologies, is that we're kind of limited by the need to communicate along the wires, send signals along the wires. How does this technology stack up when you look at it that way?
It's a very good point. I did not say it explicitly, but generating these local magnetic fields that we use for switching through fields generated by current pulses is very similar to MRAM. And we know that MRAM is power hungry, right? It is costly. One of the advantages in this scheme here is that by pumping one current pulse, we don't switch just one magnet. We can actually switch a whole range of magnets. And so I didn't have time here to talk about some of the architecture ideas, but our colleagues in computer science are thinking in terms of pipelined architectures. So clocked architectures where at each clock cycle, the next step of the computation is being pushed through. So each current pulse does not just do one computation, but it does different stages of the computation, or different stages of different computations as they get pushed through.
Let's see, do we have any other questions? Okay.
Just a short one. What's the environmental temperature range this system can work in?
Everything that I've shown you is room temperature. The sizes of the magnets that we are dealing with essentially are the same that are being used in MRAM. So it's essentially the same parameters that would apply for MRAM technology also.
In a practical implementation, how would you sense the magnetic states to get the logical outcome?
That's a very good point. I mean, obviously, what I've told you about is some preliminary work. As a matter of fact, the work that I'm showing you here is essentially 2 graduate students. What we would like to do in the end, of course, is to sense the state of the magnets with electronic means. However, in principle, again, going back to MRAM technology, this is something that we can take from what's being done for MRAM. So our idea is that one might use magnetic tunnel junctions in order to sense the states. So you can think of an MRAM-like layer stack where one layer is where the switching occurs.
And that would be like a giant magnetoresistance device.
Exactly.
Okay. Let's see if there are no further questions. Let's thank